Unshare and share again. That's better. There, now we got it.
Yep.
Yeah, maybe.
And this is from Peter, the incompetent on the technology front.
Oh, completely.
You get promoted, Peter.
Yeah, well, I'm good at directing people, but not at doing anything.
Well, I should record, right? Right. So we're recording to cloud, correct? Or record to this computer? Hello?
Sorry?
Are we recording to the cloud or this
Yeah,
computer?
we record to cloud. To the cloud.
Okay.
Is it going to be...
Yes, you're being recorded now.
Right.
Recording is on.
Go ahead, Garnet. Counterfactuals, Minkowski space, and quantum propagation.
Okay, thanks, Peter. Well, it is. I have to say, it's really great to be here. It's been a great experience for me. I just want to note that one of the things that I really like about ANPA is simply the fact that there's such a huge spectrum of views of science and math and philosophy, and it's great to sort of see it spread out. And I have to say, I do agree with Peter in his suggestion that the current stalemate in physics really is going to require a real stepping back from the current recipes that we have. So I did have noticed that there's been a bit of a theme in the conference so far, which is basically questioning what the heck it is that math is saying, if it's saying anything, and what is real and what isn't. So this talk is a little bit about that theme, and it has the perspective of basically my background with statistical mechanics. So what we're going to do is just talk a little bit about mathematics from a particular perspective. And one of the things so these two guys, two users, the lion man, oops, you were stuck. Oh, there we go. Okay, so yes, so this is an artifact that I'm told is very significant archaeologically, because it's the first known counterfactual counterfactual really in the sense that this is it's not an image or something that's representation or something that a person has seen, right? It's counter reality, it's a construction. And the thought is really that, well, this is the evidence that the person who created this had our capabilities of dealing with counterfactuals, things that really aren't there. So, yes, so previous art was representational. It's quite amazing that it's 40,000 years old. And the question is, well, is this the beginning of gods and ghosts and all the counterfactual stuff we amuse ourselves with? So that was, 40,000 years ago, roughly. The historical beginning of math was roughly around 5,000 years ago, so in the Sumerian clay tablets. So that's some hard evidence that the whole idea of counterfactuals had gone into the realm of mathematics. And of course today, science is based on mathematics. But as we all know, mathematical objects are routinely counterfactual. We don't find them in the world. They're not part of the physical world. So, for example, good old points, lines, and planes. Yes, they're fantastically useful, but of course you're never going to trip over a point or fall off a plane. But these things are in a sense, inventions. In terms of things like real numbers, well, of course, real numbers make the Lion Man look like a very tame invention. Here's something if you try to represent it in real space and each digit was about the volume of a hydrogen nucleus, then you fill up the universe very quickly and could see that. So, you know, really most of our mathematical objects are counterfactual in the sense that they don't exist in space and time in the way the normal objects do. And this sort of brings in this debate, which I have to say, Dennis's first talk was I found very, very interesting. It's interesting that you know, Kronecker, who's famous, one of whose famous statements was, "God made the universe more or less than the working in," and his student was Cantor, and unfortunately it was in the end a very difficult mixture. But when you look at Cantor's feelings of real numbers, of course, he was, you know, part of the modern step theory and thought very deeply about the whole idea of it. And so we won't get into the debate of these two folks. Just to note that they were both brilliant, they were major contributors to mathematics, but they were deeply divided on mathematical issues. And some of these mathematical issues sort of stayed put in mathematics, some sort of spilled out physics, but perhaps not as many as one might hope. So let's just make a little bit of a distinction here. So let's go over to the idea of the sort of conception of the Minkowski space. And there, every point on a world line, you know, divides space-time into, you know, future, past, and elsewhere. And the fixed speed of light in our frame means that light cones are really quite ubiquitous in Minkowski space. And the whole idea of a world line is really transporting the idea of a curve representing the center of mass in the field, please. So, what does the fixed speed of light give us? Well, it leads to the relativity of simultaneity and time dilation and length contraction. So those are things that this fixed speed of light gives us. Now, the physical effects are not counterfactual in the sense that they've been verified experimentally many times. And so the mathematical models, we believe are aspects of them simply from experimental evidence. And, you know, the thing is, mathematical description does contain artifacts, that is, in a sense, stuff that doesn't correspond to reality. And we're going to probe the world line concept, which will bring the four, you know, arguments actually that have been there for rather a long time in the mathematics. Okay, so that's the idea, and we're going to have a look at a physical system and a mathematical model of it, where we sort of all know how this thing works. And we can point out the article. So diffusion. So here, you know, when we look at diffusion, we look at this thing, and from the point of view of, you know, visually and senses, we look at that and say, well, look, yes, it sure looks like a fluid which seems to be sort of everywhere. If you stick your hand in it, you feel it everywhere. And when you see how the diffusion happens, it's this rather smooth process. And if you leave it long enough, there will be what appears to be a steady state, which will be the solute is dispersed throughout the entire thing. And of course, we have a PDE that describes that, and that's the diffusion equation. And here D is a positive, so we're not going to get excited yet because D is not mentioned. Right? And we'll just look at this thing and say, well, okay, that's the PDE, it seemed to work, but we know that the atomic hypothesis is true, and so somehow we've got to reconcile this with the idea that that liquid is really a bunch of particles. So, of course, Einstein is famous for his resolving that. And we can do it quickly and cheat a little bit, but get it quickly by just examining the idea of random walks in the diffusion equation. So imagine we have this symmetric random walk. We're sitting on a lattice with lattice space in delta x and time space in delta t, and then we can represent a probability mass function for finding the particle of particular position at a particular time. And if the walk is symmetric, the first equation just says, okay, well, if you're at x at t plus delta t, then you either come from the left or the right, either one, the probability of 1.5, so you can write this difference equation. And so you can then subtract u of xt from both sides, and then you're a little bit cavalier in the next step, and you say, well, okay, suppose we can find a lattice, and we assume that u of xt ultimately is analytic. And so we can look at it to. And when we do that, again, cheating a little bit, saying, well, it's going to look like this. We get the time derivative on the left times delta t, and the second order space derivative on the right. And so we've got delta t on the left, and delta x squared on the right. We got rid of the zeroth order terms because they were equal, and the first order term in space goes away with symmetry. So this is what we've got. And now we can see our way to the diffusion equation by saying, well, let's just rearrange this. And we have this thing of delta x squared over 2 delta t multiplying the second order spatial group. So we can look at that and say, well, look, we can see the equation emerging, provided that the lattice may be defined in such a way that delta x squared over 2 delta t approaches a constant. And we know we can do this. Is there any justification for doing that? Well, yes, there is, because random walks naturally have a scale. So if you look at random walk, you have the mean square end-to-end displacement of an n-step random walk is of order n. So this isn't about physics, this is about counting the number. It just turns out that if you have random walks, that the natural scaling is, in this way, it really comes from the mathematics. It's like the central limit theorem, in a sense, the central limit theorem based on that. So it's not physics, it's just mathematics. Well, it is mathematics based on counting. And we note that this is consistent with a mathematical imposition, but it is actually a physical counterfactual. And we think of it kind of okay. Why is that? That's because we know if we look into a fluid, when we look below the mean free path, we no longer look like a pure fluid, it looks like a bunch of building balls bouncing around. And so when we shrink, when we keep on shrinking delta x and delta t, that scaling no longer works, because the particles just seem to go straight into the gap. So this thing, this scaling operation that we put in to get the smooth PDE is a physical, it's a mathematical artifact, and it's counter to what happened here. So let's just have a look at this. If we rewrite this thing, we're saying, well, delta x squared over delta t run by 2 goes to d. If we write it in this suggested form, well, delta x over 2 is a measure of the uncertainty of where the particle is if we're treating the same continuum. Delta x by delta t is just the particle velocity at that scale. And of course, the uncertainty in the velocity at that scale will be proportional to that. So really, this is a geometric form of the uncertainty. Okay, and so here we see, well, okay, we're generating these, what Bishop Berkeley would call ghosts of the particle point. These are in a sense, in this case, artifacts that we don't expect to see. So here are some of the arguments. Well, what do these paths look like? These are the Wiener paths. They're fractals of dimension 2. So they're really plane filling curves. They have infinite length. The hopping speed is, in the limits and the boundary. This scaling, in a sense, encodes a form of geometric uncertainty today. Right? All of this stuff is there, and physicists, of course, don't worry about it. With good reason. Right? Physicists believe in fusion equation to understand well that its applicability is restricted by scale. We all know that when you look closely in a liquid for diffusion, we will eventually see, well, we've got a mean free path and a mean free time, and below that scale, the scaling gives you the PDE fails, but above that scale, the PDE is a pretty good representation. So, we have this, and physicists are well aware of that. It's actually not so clear that the an eye in front of that view. Physicists in general don't make the same sort of distinction between artifact and in a sense, realistic description. And that is because the recipe for quantum mechanics is so beautiful and elegant, but we don't know what the wave function really is. So we can't directly extract a whole lot more physics from it. Okay, so just to recap, mathematics itself is clearly counterfactual, right? Its objects don't exist. But mathematical models, particularly involving differential equations, all have special goals, just basically artifacts that relate to time scale and the concept of the limit. And this was pointed out back in the 1700s by at least by Bishop Bond. So in diffusion, those mathematical artifacts are well understood. Right? They're well understood through statistical mechanics. Right? We all know about mean free paths and mean free time, and we can happily ignore those things as long as we're on scales that don't get down low. Now the same cannot be said of quantum mechanics. Since we don't know what wave functions are or what those involve, we don't have the same picture of, well, why do we have the equation? So what we're going to do, we're going to move to Minkowski space, where there is actually a clearer picture of unit scale. Okay, so a quick recap of special relativity. Special relativity uses the equivalent inertial frames and the speed of light postulate to construct kinematics. So the kinematics are really the underlying geometry of space-time. But it's a bit of a two-part process. The mass-energy relations are obtained by enforcing conservation of energy and momentum in the presence of the two postulates. So what does this mean? It means that when you look at world lines, it's assumed that they're basically smooth, time-like curves that, in the absence of external forces, display no features particular kinetics. Okay, so if you see a free particle represented on a space-time diagram, then you can look at it and say, oh yes, its velocity is such and such. You can't say what its momentum is, because we haven't been told the mass. There's nothing in the world line that says, oh yes, the mass, etc. So then events on world lines are then just points on world lines and can be arbitrarily close together. Right? So we should immediately flag this and say, well, this is a bit dangerous, because there are no analogs of mean free time and mean free time in the world line concept. So we can say, well, look, that I just missed. Come on. So the thing that's a bit tricky about that is simply that if we really put the events arbitrarily close together, well, we know that the uncertainty principle will say do that, and the energy will go up and diverge, and so doesn't make a whole lot of sense to think of a world line for a quantum mechanics because of the uncertainty constraint. But of course, you can look and say, well, wait a minute, that's not fair. We're in classical special relativity. We don't know about quantum mechanics. But from the previous analysis in some substitution, we do know that there's a geometric form of the uncertainty principle, so we can question this on the basis. All right, so let's just question this idea of scaling in world lines. So yes, we know that an event, a point on a world line, a part of the space-time in the future, past, and elsewhere. And fixed speed of light in all frames means that the light cones provide area partitions at each point on a world line in 2D. Okay, we'll see this in just a minute. So any 2 points on a world line define, of course, an area between the 2 points, yes. Just think of the light cone. And the Euclidean area, of course, regions are unchanged under Hooke's operation. So the area is really quite important. Now, here's the problem, right? If we allow events to get too close together, quantum mechanics would say that the energy associated with the world line will diverge through length and time. Uncertainty principle, which we know there's a geometric analog in the fusion model, so we should start worrying. Okay, so allowing events in the fusion to be arbitrarily close gave us all these arguments. It gave us fractals, infinite speeds, infinite lengths. It was a bit of a merry-go-round. So in Minkowski space, this QC is special. It will roughly take the role of the mean free speed, and with the finite maximum speed comes a finite time. So we shall embed this really in a 2D space-time, and just draw pictures for it, just space-time diagram. And the reason for doing this is the result allows us to find MR for finding Fock data with practically no error. Okay, so this is something that I enjoy because it really is work through. So here's this figure. So start out on A on the left. The time axis is vertical, space axis is horizontal, and C is 1. And we're thinking of a world line that is approximated as it would be in a finite system with points. We're going to call these things events, and we're going to make sure they're, for simplicity, equally spaced. So in B, we just say, all right, just draw in future and past light cones for each of these events. There's a reason for doing that. We can look at that and say, okay, well, just take the intersections of sequential points and look at those areas. Now, those areas in C, they're causal areas in the sense that they surround, the area contains all the points that are light connected to the 2 successive events. So from the point of view of special relativity, this is a real bandit. Everything inside those areas is light connected to, is time connected to the events. Everything outside of it. So these are real boundaries for special relativity. Now, because we're going in the end to try and get quantum differential equation a smooth description of this, we're going to change the coloring a bit. And so if we go to D, we're changing the coloring so that if we look at, I don't know whether we can do this. So what we really want to do is maintain really differentiability through these events. So here we're saying these guys actually cross. And so we can think of these boundaries actually as being two close. So we have this thing which looks like a chain of causal elements. And we have to ask the question, well, what happens to the boosts? Well, with boosts, all that happens is you still have intersections of forward and backward light cones, and the causal areas become causal rectangles, and the area of those rectangles are preserved. So our inertial frames, when we look at an image of the original stationary world line, what happens is the causal areas become respective. And so an interesting thing happens. So here, just a coloring so you can distinguish in a sense, the four states of the four sides of the rectangles. So on the left, just have a look at that as a chain of causal areas. Right, and it's just sitting there, and we're going to look at I guess to use it for the nine. What happens when we look at the boosted version here? Well, in part C here, we're looking at it where we're moving to the left quite quickly and see what's happened. The event at 8 is now just sitting right at this point here because of the time dilation and stretch. And if we increase the speed anymore, we're going to go from red to seeing this yellow. Okay, and we can see as we increase the speed, we're going to see different bits of these causal areas. And as we move towards the light cone, we're going to see basically farther and farther back in time. Okay, so we can then say, well, okay, suppose we took the whole ensemble of all possible boosts. What would this whole thing look like? No, mistake. Okay, so here's what it's going to look like. So here, let's just use the two colors, red and blue. If we look at this thing and say we're going to look at this case at t to the 10, and so all of these different lines are lines of constant velocity, so they're different inertial frames. They're in a sense images of the same process but from different speeds. As we go out along the x-axis, well, we're blue. Oh, now we change to red to a short interval, blue for an even shorter interval. And we can see when you do that, if you say, well, blue is 1 and red is -1, you get a function that looks like this diagram. Now, there's nothing really peculiar in this. This is just saying, well, what happens if you take an ensemble of all possible views of this repeating periodic process? Well, if you do, you get a mapping onto the x-axis and then you put in time that looks a little bit like this. And when I first saw this, I was surprised, and it reminded me of this. This had a Feynman Higgs book on part individuals. So this one's hand drawn, and that's the real part of the Feynman propagator, and this is in the non-melted domain. So the thing is, yeah, it looks a little bit like the propagator. Let's compare them. Well, that's the comparison. That's out. It's still very close to the origin. It's about, I think, about 100, or about 500 steps out. And the thing you notice is the history map, which is this rectangular wave. It takes all of the nodes in the actual Feynman propagator, the real part. And the synchronization is obtained for a single number, and that number is used. Right, so when you look at that, you say, well, okay, so this periodic process in Minkowski space actually knows quite a bit about the propagator. Okay, so you look at these two things, and really the history map is a rectangular version of the propagator. So this, in actual fact, you can turn that around as well. The history map really also will, in the end, pertain to what we get from quantum. But let's just see why it's called the history map. Let's look at this curve. Okay, so this first part, this sort of area in here, what is that? Well, that's an image of the causal area just in the immediate path of the line of fixed T that we're looking at. The next causal area is imaged by these two guys down here. So as you go out towards the cone, you're looking at the history of the particle right out to the origin. But also notice this fact that as you get out, just in terms of plotting this, as you get near the light cone, you have to have higher and higher resolution actually to make it out. So the space-time itself, in the end, is going to have sort of infinite resolution to be able to resolve the history all the way back to the unit of the Okay, so the history map versus the Heinemann propagator is simply a mapping onto space for the two-valued function representing the edges of the causal areas. And so this strongly suggests that wave function in general is just smooth versions of the history map. Okay, so recap. So the arbitrarily small inner scale of path in diffusion is well known as a mathematical. We know it true. Adding the finite mean-free path to the kinematics of the Minkowski space to a world lines of particles in the Minkowski space produce a history loop, which is simply a discrete form of the Heinemann propagator in the non-relative going where V is small. So in a sense, if we back up a bit, that tells us, the history map tells us really what wave functions are, in the sense that codings of the history of the particle. Okay, so, and the highest resolution was the origin, the lowest was highest resolution near the origin at a particular time you are, the lowest, you need a higher resolution actually to get at the details as you approach the light. Okay, so the synchronization over terrestrial speeds relies on just a single number, that is the mass. And the history map is just a Lorentz transformation in the discrete world. So there's no formal information or quantization. So we're talking about, in a sense, two different things. One is from the classical relativistic world, one is not. Okay, so if we just look at the figure, we can see the transition to the continuous is really hard. Okay, so translations from known material. What is this? How do we fit this into what we already know? Well, the 2D version is, in a sense, a reformulation of the Heinemann chessboard model. And if we look down here, we can see where it comes from. So on the left are the oriented areas. If we just split this up and say, okay, consider everything to the right of the right of the events, we can say, oh yes, this is just a chessboard map, and oh yes, it has period core. If we look at this, it goes right, left, blue, and then over to right, left, red, so period 4, and so it's Heinemann's corner rule. I for every corner is, is a simple way of coding. Okay, so alternatively to the final chessboard model, you can actually code the digital images of these causal areas so that you can see them. So you just do a little bit of digital image processing. You smooth that out, and you can then actually extract the black effect. And so you might find it peculiar to get the black equation in the context, but it's very easy to do, and it sort of gives you this other way of seeing what the Dirac equation is doing visually. Okay, so the other thing is that the chessboard model, which we can see where it comes from the causal areas, we can see why it works, but really what it's encoding is really area rather than the length. So yes, it's a path integral formulation, which Feynman invented because he came up with this lovely path integral for non-relativistic mechanics. But in this context, in relativistic sense, we can see where it comes from straight from the property. Okay, so translations to the derivative. This was this eigenvalue to the velocity operator by plus or minus. So we can see this in the model because it's a manifestation of the fact that the area boundaries are like things. And stepping back a long way, we can see that actually practically all the effects that were unearthing from a point of view of people, our senses, is because we are large mass objects, and all of our senses average. Okay, so all of this stuff is below our ability to detect things. So, for example, the whole concept of being stationary or at rest, for us is an actual concept, when in actual fact, for a particle, you have to create rest by balancing the light length. So the only thing that is, in a sense, at rest for particles are the light lengths. And so, in a sense, we're controlling velocity through the light lengths. Yeah, so particles have to construct stationarity from their causal elements. Okay. The other nice thing is the 2D modeling explicitly points to the extension theory. It's half a page to find out, yes, this does extend the theory. The other thing that this makes pretty clear is that the graph equation has this sort of peculiar feature that it's embedded in 4D, but all the interesting stuff happens in 2D, and the 2D is our space-time planes. So you can see why this is sort of directly used. And as to, there's always been this question in quantum mechanics, in the path integral reminded everyone so much of diffusive modeling, the fact that how all these powers and taking ensemble habit. But then in the diffusive case, there really are all those paths because you've got many active particles giving you the path, whereas in quantum mechanics you have one. Well, the reason is a bit different for a particle in Minkowski space is that those paths, those causal areas, they're just images. Right? They're images that space-time has to be able to support because you can look at these things from different velocities. So the sum of the path is really mimicking a whole ensemble of paths that can all be registered to be stationary. And so, in this sense, the Dirac equation is as per Wheeler, space-time having a particle move. But this particle identifies its mass by an inner state. Unlike in special relativity in general, where there's no identifying feature in the kinematics over that document. Okay, conclusions. Most of the smoothness our senses detect in the world is because of massive error. That's why, as individuals, when we think about rest and uniform motion, with rest being in a sense special, because it is for us because we're massive. The classical PDEs that give smooth solutions encode some form of smooth. We know that. While we know below that, nature is rough. The diffusion telegraph equations, if you think about the molecules that are in the fluid, their motion is rough, but the scales are uniquely rough. So, yeah, in classical physics, we understand this, right? Because we know the statistical mechanics, and we can happily ignore the mathematical arguments. So here's where it gets a bit tricky. In non-relative quantum mechanics, physicists often embrace light. Things like many worlds and infinite signal speed and the uncertainty principle on moral scale. All of those things, if you switch to the classical picture, you say, oh yeah, well, yes, those are artifacts. Forget them. Now, in quantum mechanics, you can't. You don't know what the wave function is in quantum mechanics. Physicists tend to speculate on quantum mechanics on the basis of non-relativist quantum mechanics, which has these things. Okay, so yes, building an in scale in world lines allows you to see that the ubiquitous phase of wave functions is actually a residual, a relativist mechanic. So, going through the process of looking at world lines and saying, yes, the events allow events to get within a constant a wavelength of each other but no closer. So we build in a scale in kinematics that leads pretty quickly to things that look very like. Yeah, so wave functions themselves then are, they come from the whole idea that space-time gives you the geometry of how we do things. Okay, so there's just a visual analogy of machine history. So, any questions?
Okay. Thank you very much for that, Garnet. So, have you got a question? John and then Chris.
Hello, Garnet, that's really fun. I enjoyed watching the full presentation there. I've seen bits of it before, but it's lovely to see it all in one continuous part. There's one thing though that I think you may not need, and it may be even more beautiful to do it in a slightly different way. The difference between when you go to the diffusion equation, where yes, the constant that's coming in is a mathematical construct, and when you go to the Schrödinger equation, is the way you go to the Schrödinger equation is you come in with a wave function which is smooth, and you have smoothness there at the level at which you introduce it in the wave function. Now, it's interesting because the dichotomy in quantum mechanics, where the uncertainty relation, it's fashionable to think of the uncertainty relation as being something which is itself not smooth, but can take any value between plus or minus half h bar or whatever it is, for the particular whatever scale it is for the particular energy one is looking at. But I don't think you need to get away from the smoothness for the Schrödinger equation, because what you're doing is you're bringing in a length scale, but the kind of length scale you're bringing in is different to the diffusion equation. And the diffusion equation is a mean free path. It sets some sort of scale, but it can be big or small. One knows that one gets stochastics on that. But in the Dirac equation, you know, you're bringing in a zitter vapor, which is really just going backwards and forwards smoothly.
Yes, okay, but John, think of, okay, if you think of how we got to the diffusion equation, and we notice, yes, it's smooth, but it's the solutions are smooth, but it's smooth because of a sleight of hand. And we took that scaling relation and said, just take the limit as delta x and delta pt goes to 0 in such a way that delta x squared over delta t approaches a constant.
Yes, I know, that's right. But the difference in quantum mechanics as you observe it is that if you look at wave functions, which you can do in the solid state, they are smooth.
Yes, they're smooth on the scales in which, well,
they're smooth fractions of
John, when you say they are smooth, do you mean anything other than they appear to be smooth at the level of observation that you use?
Yes, I do, but the level of observation one can use is very much shorter than the wavelength. So they're smooth at 1 part in 1,000, which is about as far as I've gone down looking at them. We have to observe them to be smooth at that level. So you see the whole shape of the wave function, the whole beautiful. I read a paper on this in 1990, a Fisher paper. So you can look at these things, because what you do is you build a device which is small compared to the wavelength, and then you move that effective device, it's an electrostatic device, you can move around over the wavelength. So they are smooth. But you see, I think that it's even more beautiful if you do it smooth, Garnet, because...
Oh, okay. So, John, I have to disagree with you there, because, yes, okay, think of going from this whole perspective. Let me just go back a little bit, and I'll show you what the issue here is in picture. So you may ask the question, well, what the heck is the de Broglie wavelength? Well, actually, the de Broglie wavelength, when you look at this thing, it's the distance from. Can you see that little hand?
Yeah, I can. It's distance from one point to the next one. Yes.
Yeah, it's from here to where the next event gets stretched out. So there's a very different. So there's a very different scale. Now, when we look at the diffusion equation, we say, oh yes, it's beautiful. The solutions themselves are smooth, and blah blah blah. But we don't believe them when we get down to the scale of the mean free path.
Yeah.
Right? The mathematics is fine. Everything's smooth, right? So if we extend that analogy to Schrodinger's equation, yes, we'll get smooth solutions. Yes, we will, because the differential equation is smooth. You built it to be smooth, but that smoothness is built on an artifact, and the artifact actually relates to the uncertainty. The uncertainty principle holds.
Yes.
Everywhere and anywhere, and we know that if we take those solutions and we compare them in a situation where the speeds are anywhere near the speed of light, we can go, oh, doesn't go up too bad. We have to go to the Dirac equation, and that we will also find that is true for the diffusion equation. If we go down near the mean free path, we see, oh yes, the diffusion equation now no longer works because it's constructed with this artifact built into it.
Right? No, I understand what's happening with the diffusion equation, but I think what you're effectively doing when you go to the de Broglie wavelength sizes here is one still has a discreteness, but now the discreteness is precisely timed, click, 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 which you describe here as events. But I would describe it as a thing just coming around and getting back to 2 pi or 4 pi for a fermion, coming around to 4 pi. So you have that discreteness, and I think if you still have that smoothness, and I think if you put the smoothness in, what you're doing really is you're going from your boxes to your circles in your diagrams. And you're going from the square edge diagram on the bottom right there to that one which is smooth, the final propagator diagram. And I think that will simply come out going from something which is constrained by being within the light cone to being constrained by having a circulation going on inside it. There's a Vegan circulation.
Okay. I mean, I agree with that, except you're then stuck with the question with, how the heck does that happen? What is it that actually gives you that? Whereas when you look at this thing, when you look at it this way, you say, I'm not interested in quantum mechanics, I'm simply just going to put in this thing. And when you do that, you go, oh, this pattern, I've seen that before.
Yeah.
And then you have to ask the question, well, okay, if you've seen that before, it's not quite the same, it is smooth. So how the heck do you get the...
I think you get it more naturally, because at the moment you put a series of events in which are arbitrary. You've chosen to switch time up to series of events, but these are not events. An event is what something, you get a quantum collapse of a wave function, and the set principle does do. In this case, we're just looking at splitting your world line up into discrete points. But if you do that with the Compton frequency, then you have a natural frequency for that split.
That is it. It's the Compton frequency.
The Compton frequency. And then you don't have to stick events in. You just say it comes around in the Compton frequency. Click, click, discrete, beautiful.
Okay, that's true. If you think in as you said, right? Thinking in real space is different from thinking in frequency space. If you think in frequency space, you look at that and say, oh well, darn right, I don't like all those high frequencies. If I smooth that out, what's going to happen? Well, what's going to happen is I'm going to smooth out those edges. It's going to become a continuous right at the discontinuity. And then when you look at it in its Fourier transform, it all works out beautifully.
I think it'll work for you just as well without having to have the conclusion that it should be that it doesn't need to be smooth at that level. You've got a clock there, and natural clock, and the natural ruler.
Okay, so let me put it this way. What this stuff does, at least the reason for this, is I'm asking a question. I'm saying special relativity is gorgeous. It works like a charm. How the hell is it quantum? You look at it and you say it's coherent. It's beautiful. It does what we need, but in this quantum, how does it? So when we look at this, we say, well, okay, this is about events. You get fun. In mutual production conditions, we say events all have points. Well, they sit on lines, and of course we know in the history of mathematics that's a line isn't really a collection of points. We have to fudge
Yeah, that's right. And for a real particle, if you've got something which really does have a characteristic frequency, you really should put that discreteness in.
Yes.
Okay.
So here, maybe an alternative to this is to say, how did space-time miss one? And we can say, as according actually to your model, it misses it because it misses the fact that the mass occurs in kinematics.
Yes, mass occurs in the frequency space. Mass is in frequency space. That's
okay, and if you map the frequency space back to the real space, you say, oh yes, there's a sting. And if something does that in real space, you have these.
You have those light curves, and then you have circles. When you put circles inside them, I think that's even more beautiful. That's what I mean. It's your talk, so you're talking about what this is, but that's what I'm getting from what you're saying. Is that correspondence between what's happening at the Zitterwegen level and your events?
Okay.
That's the thing to do with them.
Can we have other questions? We need other questions.
Yes,
Chris.
Yeah.
So you showed a one space plus time dimension, and you said that it extends to one space plus 4 plus 3, 3 space plus time. Is that because the propagator is the product of propagators in the 3 space directions? I just want to confirm that.
Okay, so a quick and dirty way to see that you can extend this to 4 dimensions. That you don't immediately see from the chessboard because you're fiddling around with the paths. Is that when you formulate the thing, you associate space with sigma x or sigma y. You have this switching mechanism that actually allows the particle to go back and forth, right? Because it goes back and forth in space. So you have one of these nice matrices to do that, and you associate momentum with that direction. Well, in the end, that was an instruction that when the homogeneity of space, you can say, well, that can be anything. And how do you put that in? Well, the P becomes the length of the momentum vector, but the actual direction is given to you by, you have to go through a four-stage process in this. It's one of the, you know, the alpha matrix or gamma matrix, whatever the formulation is that you choose. And so in this formulation, you can see, you can write down what the 4D graphication is from the 1 and 2D. And you can see in the end why it is that you can do that. It's not expected because, from the Planck interval, because the Planck interval was invented as a Planck interval, and everybody thinks of them as the Planck particle. But in actual fact, no. The Planks themselves are a right or left envelope of the causal areas that you get in the events. So it's a once you see that, the 4D to become.
Okay, can I ask another question? Nicola?
Hi.
Very quick.
Yeah, well, mine's just a kindergarten question. How come these things are called causal areas?
Okay. It's called causal areas because the area between the events, which is outlined by those diamonds, they're timeline connected to the two events. So anything in those areas can affect the subsequent event. Where outside those areas, they can't affect that event because you can't have propagation faster than the speed of light. So how do you define causality? Because you don't have any speeds that exceed light, you can't have something outside those causal areas directly affecting the subsequent event. So the thing about this model is that from the point of view of special relativity, those areas in a sense are real, in the sense that you run this by somebody who does it relatively funny. Yeah, that's a causal area. It's something that will be associated to successive events on a world line. And if you pursue that with somebody who does relativity, and you say, okay, well, what happens when we bring those two events closer and closer together, so the area gets smaller and smaller? Well, the physicists will get more and more nervous because they're also thinking, you can't do that with quantum mechanics. You're going to get vast energies associated with that distance. So, I mean, we sort of take care of that by saying, all right, build in a single characteristic length, and it's the complement. And the surprise is, at least people tend to be a bit surprised, that the complement length is tiny compared to the Boy length. And this is the Boy length that actually is present in chemistry. And so you think, oh, how the heck is this funny thing that the complement temperature actually generates the stuff at this much larger scale that the Boy wavelength. And the reason is this diagram down here. When you look at this, you see this central bit here. That central bit is the image of the recent past of the particle. It's put together from all possible different speeds, and that spreads out and gives you the scale for the de Broglie wavelength. So you have this funny feature of sort of zooming as you get farther away from the source, you have this wavelength that's associated with this flat region which spreads out, and that's the region that gives you in a sense, that interactions can take place.
Okay, thanks very much for that, Garnet. Could you take your screen off now, please, so we can go on to the next?
Thank you.
Another applause.
Thank you.
So, our next speaker is Chris Thron.
We can probably take 2-3 minutes while I...
Yes, certainly.
Yes.
I'll just introduce your talk while you're waiting. A non-causal reconceptualization of quantum field theory.
Oh.